The title of my paper is Copper Catalyzed Crystallization of Amorphous Carbon into Graphene. So graphene is one thing which is very important for the scientists nowadays because it's a very important 2D material, and a lot of research has been done in the field of graphene, and in future many people will come up with more research work, I suppose. So I'll start my work by presenting in the outline. So I have the introduction about graphene, then why we did this work, what motivated us to do this work. Then I'll share the experimental design where I have different configuration of my structure that I took. And then the annealing parameters, because the most important factor to form graphene is to anneal in my case. And then the Raman characterization, which proves the presence of presence of graphene, beg your pardon, and the inference from the various characterizations that I got, and then finally I'll discuss the mechanism and then I conclude. Okay, so the first important point is graphene. It's very important because it has excellent properties, excellent electrical properties, thermal properties, and because the most important thing that, as you can see, it's a 2D material and it's one atom thick, and also you can see here there's no band gap, so the electrical conduction is very high in this particular material. And also various methods right from 2004 after its discovery has been followed up, and the most important method nowadays used is the CVD. As you can see here, the CVD graphene gives a very high quality graphene, and also the price for the mass production is very low. And other methods like exfoliation of silicon carbide or liquid phase exfoliation or molecular assembly, these have a lower quality, and this particular material of mechanical exfoliation was the first method which was used to discover graphene, though it has a very high quality, as you can see, but the price for the mass production is very high, because if we talk of small domain graphenes we can get very easily, but if we talk of mass production, it's not quite feasible with this method. So people have been working on different methods to obtain graphene, and the most recent and the most simple method is of course CVD, but it requires a lot of expensive gases like hydrogen, methane, and it's dangerous also. So people have been modifying CVD equipments to get a better method to develop graphene. So so what motivated us? So we have some methods reported by people which talks about crystallization of amorphous carbon on nickel and cobalt. But they clearly state, as written here, that graphene synthesis is not possible with copper when it comes to crystallization of amorphous carbon. So this really motivated us because copper is very important, and these are the references which talks about taking amorphous carbon underneath nickel and then crystallization parameters, and then it crystallizes to graphene on the top, and also cobalt and nickel with amorphous carbon and it forms graphene on the top. So what motivated us is because copper is a very important material in the field of interconnects, and we cannot neglect any possibility of graphene formation on copper. So we have to take care about that, and also we try to investigate the reasons and the phenomena why this particular method is not feasible when it comes to copper, and if it is possible, then how. So I'll introduce with the experiment design. So we took a lot of configurations of different structures, and we came up with first sample, which we name as sample 1, and it has SiSiO2 having amorphous carbon, a 60 nanometer amorphous carbon on the top, and then we had 1.2 micrometer copper, and this is the process steps that we follow. First we sputter 12 different thickness of carbon by using these parameters, as you can see, and then we had sputtering of copper on the top, and then we anneal them. So the annealing parameters I'll discuss later. So the most important parameter over here is we anneal it for 50 minutes at 1020 degrees Celsius, and the hydrogen flow is 50 SCCM. So as you can see, the temperature, then the pressure is maintained to 1 torr and hydrogen flow 50 SCCM. First we ramp up for 60 minutes up to 1020 degrees Celsius, then we have a constant anneal time for 50 minutes, and then we cool down. So this is the annealing parameters, and finally after that we get the Raman characterization. So I'll first share the reference Raman which is already presented in the earlier work. So two most important things over here to see is that first as the energy of the Raman laser that we use to detect the graphene, it increases, there's a shift in the Raman. And also when the number of layers of graphene increases, we can see there's a shift in the Raman. So this thing is very important for our data that we got, because normally if we take the reference for the pristine graphene, then the D peaks, G peak and the 2D peak is at about 15, 18, 2670, taken at this particular nanometer laser wavelength. But what we got was 2726 and 1585. So this particular shift, as you can see here, this 2D peak, this shift is just because we are taking the Raman measurement at 473 nanometer. And also we get I2D by Ig ratio of 0.29 and ID by Ig ratio of 0.49 in sample S1. So this particular ratio of I2D by Ig represents that there is a multi-layer graphene present. Because if this ratio is less than 1, then there are chances of multi-layer graphene present. So after investigating this sample S1, we found that graphene can be deposited on copper by using amorphous carbon crystallization. So, but the problem was the graphene that we got was not really single layer and not of good quality. And even the D peak was very high, the defect was very high. So we thought that maybe because of a lot of carbon is present, so let's decrease the thickness of carbon and then check. So we took two more samples, S2 and S3, with 36 nanometer and 12 nanometer amorphous carbon, and rest the process was exactly the same. And the only difference was during annealing, we took different annealing time. Now this is a very important point because already reported data that say that with copper this method is not possible. They have said they haven't taken annealing for more than 5 minutes. But we took annealing for about 10 to 15 minutes and we observed at different point of time and we could see a mechanism coming up. So again, the annealing is exactly the same, the only difference is the anneal time. Okay, so out of the Raman data that we got, we have for the first inference. So the green graph that you can see is for the sample S2 and the blue is for sample S3. And this one shows the I2D by Ig ratio comparison. So in the first, if I talk about sample S2 with a thick carbon, in the first 10 minutes we have nothing and then slowly it grows up and goes down. So what happens is that slowly this carbon is trying to convert into graphene because of hydrogen interaction, and then at this point we have the maximum quality graphene, and then it goes, there's a drastic decrease because all the graphene formed here is etched out by the hydrogen present. Because hydrogen has a dual role, it not only helps carbon to form carbon species for graphene deposition, but it also etches out graphene. So it's a counterbalance situation. And this is the average surface roughness taken by AFM. And over here also you can see, like if I zoom this point to here, we can see that for sample S2 the roughness is higher and for sample S3 the roughness is lower because sample S2 has a thicker carbon, and during high temperature annealing it experiences less thermal stress, while the carbon, because there is reported work on Stoney's equation which says that thicker the film material is, lesser the thermal stress it will experience. So, so the sample S3 it experiences less stress and the sample S2 experiences more stress. So, sample S2 experiences more stress. So we have this data, and slowly in both the cases, in the green and the blue one, both cases, there is a slight increase over here. The increase is here, and for the blue one the increase is here, and then there is a decrease. So this increase and decrease is again because of the carbon sitting at the bottom coming up, it forms roughness, and then when it crystallizes to graphene, it becomes smooth. So now we move on to the mechanism. Like there are two important aspects of the mechanism. The first one is hydrogen, which not only acts as the CHX radical form, like the reason why we form carbon species, but also it etches out graphene. So we have to take care of about the hydrogen and the amount of hydrogen we are using. And the second governing reaction is this hydrogen reacts with carbon to give carbon species, and also it reacts with the native copper oxide to only give copper. So the mechanism can be understood by this, like we have this structure. I'm talking about sample S2 with a thicker carbon, and we have a native copper oxide on the top initially. So when there is a room temperature ramp up to 1020 degrees Celsius in the presence of hydrogen, So what